Now we'll study about the applications of potentiometer. Now basically we need to study over here three applications of potentiometer. The first application is it is used to find the EMF of a cell. The second application is it is used to compare EMFs of two cells, and the third application is it is used to find internal resistance of a cell. Now we'll study all these three applications one by one. In the very first case, we'll study how to find the EMF of a cell. Now, in order to find the EMF of a cell, what we need to do over here is, first we need to connect a cell of known EMF, of a standard known EMF in the secondary circuit. Now say, this is a cell whose EMF is known to us. So what we do is, we connect this cell in the secondary circuit, that is, we connect the positive terminal of this cell to A, negative to galvanometer, then a resistance box, and then a jockey, and we find the null point. Say we get the null point at point N. Now, if we are getting a null point at N and say the distance from A to N, this AN distance say is L, then we can say that the EMF of this cell, say this is the EMF of the cell E, small e. So this small e EMF of the cell is directly proportional to L, length. Now see why we can say so. Say the potential of point A is VA, and the potential of this point say is V plus. Just the positive terminal of the battery is V plus. Now since no current is flowing between A and this terminal, we can say that VA equals to V plus. Similarly, say the potential of point N is Vn, and the potential of the negative terminal is V negative. And since no current is flowing in this circuit also, that is from N to the negative terminal, we say that Vn equals to V negative. Now when I subtract these two, that is Va minus Vn, I get V plus minus V negative on the other side. Now Va minus Vn is nothing but the potential difference between the 2 points Van, and V plus minus V negative is nothing but the EMF of the cell. So over here what we get is that the length which I get, that is the An, this length, balancing length, is directly proportional to the EMF of the cell. Now, when I divide E with L, that is the EMF which I have got, the known EMF, and the L, I get a constant K, and this K is known as potential gradient. Now the very first step which we did here to find the EMF of a cell is, the very first thing we did is we have find the EMF, we have find the potential gradient of the potentiometer apparatus. Fine. Now the next step which we will do over here is we will connect the cell whose EMF is not known to us. So in the same circuit we connect the cell of an unknown EMF, say this is E dash. Okay, now E dash is not known to us, this is what we have to find. Now the balancing length which we get over here say is L1. Now we can write that, say AN in this case is L1. So I can write E dash is directly proportional to L1, and since we know that E dash equals to K times L1, and K is nothing but the potential gradient which we have already calculated earlier with the standard cell. So when I replace the value of K over here, I get the EMF of the unknown cell. Now this completes the first application of the potentiometer. Now we come to the second application. Now the second application is where we have to compare the EMFs of two cells. The second application is to compare EMFs of two cells. Now for this, let's see how we make the circuit. Now the circuit which we make over here is, say this is first cell whose EMF is say E1, and this is second cell whose EMF is say E2. Now we connect both the cells, that is the positive terminals of both the cells, to A terminal, and the negative terminals of both the cells is connected to a two-way key. That is, this is a two-way key, 1, 2, 3. Now from the middle terminal of this two-way key, we connect this to a galvanometer. Galvanometer is connected to resistance box, and then the resistance box is connected to a jockey. Now the very first thing which we will do over here is we will connect 1 and 2. We will connect 1 and 2, but we will not connect the 2 and 3. Now the moment we connect 1 and 2, what will happen? The first cell comes into the circuit while the second cell is still out of the circuit. And for this circuit we find the balancing length. Say we get the balancing length again at point N, and we say that AN say equals to L1. Now we can clearly write that the EMF E1 is directly proportional to L1. Now the second step which we do over here is we will disconnect 1 with 2 and connect 2 with 3. Now in this circuit, E2 is now connected to the circuit and E1 is out of the circuit. And say for this case we get a balancing length at N dash. N dash is the new null point. Now we can write over here, say this AN dash equals to L2. That means E2 is directly proportional to L2. Now say this is 1, this is second expression. Now when I divide expression 1 and expression 2, I get E1 upon E2 equals to L1 upon L2. And this is how we can compare the EMFs of two cells. Now, one thing I just need to tell you over here is that this resistance box which we are connecting over here in series with the galvanometer. Now this resistance box, or whatever the resistance which we take out from the resistance box, will not have any effect on the null point. See, even if I take out the 10 ohms resistance and then afterwards I take out the 20 ohms resistance, it's not going to affect the null point of the system. Now this resistance box is attached just to protect the galvanometer. It will not affect the null point. Now since galvanometer is a very sensitive apparatus, so if I place a jockey somewhere, some other points which are far off from the null point, then a high current will might flow through the circuit, which might damage the galvanometer. So just in order to protect the galvanometer, this resistance box is connected in series. Now we come to the third application. Now the third application of potentiometer is to find the internal resistance. Now how do we do that? Now let's talk about the third application. To find internal resistance of cell. Now for this, the circuit which we make is again very similar to the circuit which we have just made, with just a minor change. That is, instead of the second cell, we put one resistance over here. Say we call this resistance A as S. And this resistance is connected to, again, a two-way key, that is to the third terminal. And say the cell which is connected has an EMF E. Other things remains the same. I'm just rubbing this just for time being. Now, our circuit is now ready. Now again here, the first step which we will do over here is we will connect the terminals 1 with 2. We will not connect the S over here. We will simply connect the terminals 1 and 2. That means now the cell is in picture and this resistance box, a small resistance box S, is out of the picture. And say over here we get the null point at N such that AN equals to L1. So I can write over here that E is directly proportional to L1. Say this is expression 1. Now we come to the second step. In second step, what we do is, we will not disconnect E from the circuit, but instead we'll connect 2 and 3 as well. Now we have both E as well as S in the circuit. Now if you see over here, what has happened is, now the moment I have connected the S, the current will start flowing in this circuit. Even if this jockey is at a null point, then also we'll have a current which is flowing within this circuit like this. Okay. Now that means when I find the null point, say this time the null point obviously will not be N, it will be say over here. Say we get the new null point as N dash. So now this time the AN dash, which is L2, now this L2 will be directly proportional to the terminal potential difference. Now see over here, since the current is flowing in this circuit, that means the potential difference, that is AN dash, will be equal to the potential difference across, say, this resistor S. And when the current is flowing through the external resistor S, then the potential difference across S will be equal to this terminal potential, which we represent by V. So here we get the second expression where V is directly proportional to L2. This is the second expression. Now when I divide 1 and 2, I get E upon V equals to L1 upon L2. Now you must have studied the formula for the internal resistance. Now the formula for the internal resistance, if you remember, is say small r equals to E upon V minus 1 into capital R. Now this formula basically is valid for the circuit, say like this, which has the external resistance R, a cell which has an EMF E, internal resistance small r. Then the potential difference across the R, say, is B. Now for this circuit, the internal resistance which we calculate is E upon V minus 1 into capital R, where capital R is the external resistance. Now if you compare this circuit with this one, you'll find it exactly the same. Just instead of an R over here, this external resistance R, we are using an external resistance S. That is the only difference. Now if I use the same formula for the circuit, I can write the internal resistance R equals to E upon V minus 1 into S, and E upon V is nothing but L1 upon L2. So I can write small r equals to L1 upon L2 minus 1 into S. So by this we can calculate the internal resistance of the cell.